This is the entire program for Goldbach conjecture. The Goldbach conjecture has three functions, which is like main function, and to find the prime is prime C function, and to find the Goldbach of the number is the Goldbach function. While executing this program, we just get a output in the form of Goldbach conjecture as expected for numbers from 4 to 100. Each of this is a individual prime number for all even numbers ranging from 4 to 100. On to the next question. Explain the nested loop in which you find two primes to sum the integer. The loop in which we find two primes to sum the integer in the Goldbach function is here. Here the loop iterates over all possible values from p to n minus p, where n is an even number which is given as the input from the main function inside the for loop. For each value of p, it checks if both p and n minus p are prime using boolean, whether if the boolean value gives true, it is a prime, else if it gives a false, else it is prime. The is prime function returns the boolean as false or true from the is prime save method. If they are both prime, then it prints the sum of two primes and returns from the function. If none of the values of p satisfy this condition, then it prints no solution from here. Moving on to the first question of the assignment, highlight the main loop in which you iterate over the integers 4 through 100. Here is the main loop for the entire Goldbach function. Here the for loop iterates from 4 till 100 with the skip of 2. It ranges from 4 till 101, since the for loop always counts as n minus 1. So n minus 1 will give you, that is 100 minus 1 will give you 100 numbers. So with a skip of 2 numbers, because we are just looking for even integers, and once this for loop is being executed, Goldbach function is called, and the value which is in the first range is 4 is being passed to the Goldbach function, which goes again to this function, and which again in turn calls the prime sieve of n. Prime sieve of n again will give you prime sieve of 4. This 4 will be passed to the 4, and it will calculate whether it is a prime or not, and after it is calculating prime or not, it will come back again to Goldbach and checks the range in p. If both primes of p and n minus p are true, then it will print the values as n equal to values of p will be initially 2 and n will be initially 4, and n minus 4 will be giving you 2. That's why it gives the output. That's why it gives the first output as 4 is equal to 2 plus 2. That's why it gives the first output as 2 plus 2. 4 is the n, p is 2, and again plus in between n minus p, that is 4 minus 2 will give you again 4. Moving on to the third question, show the recovery of prime numbers. How can you optimize this? The ancient Greeks around 2500 years are usually credited with being the first to study prime numbers for their own sake, but Eratosthenes devised an algorithm for finding all prime numbers up to a given limit known as sieve of Eratosthenes method, and even Euclid provide many important results about prime numbers. The is prime of sieve function is defined based on sieve of Eratosthenes method, and there are several ways to optimize this code for speed and memory efficiency. Let's discuss about the three methods to optimize. In the S prime C function, we can start the loop from I is equal to 3. Start the loop from I is equal to 3 instead of 2, and increment I by 2 instead of 1. This way we can skip checking all the even numbers except 2, which are obviously not prime. And the same function we can also start the inner loop from j from j star I instead of j is equal to I star I plus I, and increment j by I star 2 instead of by I. This way we can skip checking all the even multiples of I which have already been marked as non-prime by previous iterations. In the Goldbach function, we can use more efficient ways to check in if n minus p is a prime or not. Instead of using the list of booleans written by the booleans written by the is prime method, the function which takes O of n spaces and O n log of log n spaces time to generate. We can use a simple function that checks if n minus p has divisors up to its square root. This takes O of 1 space and O of square root of n time per check.